All right, today's warm-up. There are two problems. I want you to go ahead and give both of them a shot, and then come back and check and see how you did. All right, let's see how you did. We have 3 to the 3x plus 6 is equal to 27 to the x plus 2. And we already realized that, 3 is a pretty low prime number. The likelihood of it being able to get any smaller? Not. We should realize, though, because we memorized our perfect squares and our perfect cubes, that 27 can be created by 3 cubed, where 3 will give us an identical base to our value on the other side of the equation. Well, 27 is 3 cubed. 27 was being raised to the x plus 2 power, and so that will be equal to 3 being raised to the 3x plus 6 power. This is where our exponent laws become so very important to us, because we need to recognize this as a power being raised to a power. And when you have a power being raised to a power, you can multiply the two powers. 3 times x plus 2. And so we would distribute 3x plus 6. So on the right side of the equation, we really have 3 raised to the 3x plus 6. On the left side of the equation, we have 3 raised to the 3x plus 6. Now, it doesn't matter what value I put in for x. Every value for x will satisfy these equations because these equations, because the expressions on both sides in the powers are identical. So we would simply say all real solutions. Number 2, identify the mistake. Now, sometimes it's advantageous to rewrite the problem. And work it out from scratch. Now, 1/8, I would go ahead and recognize that 8 has a power of 1, and I want to bring it up into the numerator. So that would give me 8 to the power of negative 1 raised to the 5x power. Well, let's go ahead and clean this up and get rid of the power to power, because obviously I'm going to have to break down 8 into a smaller number. So negative 1 times 5x gives me 8 to the negative 5x power. But 8 is a perfect cube. That's 2 cubed to the negative 5x power. So we have another power to power that we can clean up. Well, 3 to the negative 5 is negative 15, so we have 2 to the negative 15th power. Now, let's check and see how similar things were. That step looks identical. This step looks different. Well, what's different about it? We have a positive 5x, and we really should have a negative 5x. And so the rest of the problem from that point forward is going to be wrong. Today our focus is going to be on solving exponential equations. And so 2 steps for solving exponential equations. First, express both sides in terms of the same base. Second, when the bases are equal, the exponents are equal. First, express both sides in terms of the same base. Now this is what we did yesterday, or saw a lot of yesterday. 7 to the x is equal to 7 to the 5. Notice we have same bases. Step 2, when the bases are equal, which they are, the exponents are equal. So I can set the exponents equal to each other. X is equal to 5. So let's do some examples. 5 to the second power raised to the x power. So first thing I want to recognize is, hey, I have a power to power. I need to use my power to power rule, which asks me to multiply the powers. 5 to the 2x power. And that's going to be equal to 5 to the 1/2 power. Well, since I have like bases, we set the powers equal to each other. 2x is equal to 1/2. We'll divide both sides of the equation by 2, and x is equal to 1/4. Solve 4 to the 3x plus 1 power. Now, the most common thought is to think that, hey, 4 is our base, we need to make 32 our base. So we'll divide 32 by 4 and get 8. We'll divide 8 by 4 and we get 2. And we divide 2, wait, we can't divide 2 by 4. It doesn't equal 1. Well, since it doesn't equal 1, we're not really looking for a base of 4. Well, what possible base could we have in common between 4 and 32? Yeah, hopefully you're thinking 2. So let's try that. 32 divided by 2 is 16. Divided by 2 is 8. Divided by 2 is equal to 4. Divided by 2 is equal to 2. Divided by 2 is equal to 1. And so notice we end up with our string of 2's down here on the bottom. 1, 2, 3, 4, 5. 32 is the same as 2 to the 5th power. Well, now we need to figure out how to make 4 have a base of 2. That's going to be 2 squared. Well, 2 squared is 4, and 4 was raised to the 3x plus 1, so we need to continue to raise it to the 3x plus 1. And now again, we have a power-to-power rule that needs to apply. So multiply the two powers. 2 times 3x is 6x. 2 times 1 is 2. So on the left side of the equation, we have 2 to the 6x plus 2 is equal to 2 to the 5th power. We have finally made the bases identical. Since the bases are identical, we can set the powers equal. 6x plus 2 is equal to 5. And at this point, it's a two-step equation. You shouldn't need a review of this, so we'll solve that real quick. 6x is equal to 3. Divide both sides by 6. And x is equal to 1/2. Next, 16 to the x is equal to 1/4. All right. Well, most notably, I see that 16 is a perfect square. So I'm going to go ahead and play with that. 16 is the same as 4 squared raised to the x, where we have power to the power. So that would be 4 to the 2x power. But what in the world can we do with 1/4? It's a good idea to remember that 1/4, the 4 has a power of 1, the 1 has a power of 1. I don't really care about 1 to the power of 1 because 1 to the power of 1 is 1. It's going to eventually simplify out somewhere. But I do care about this 4 to the power of 1 because if this 4 to the power of 1 were not sitting down here in the denominator, it would be a common base. Well, hopefully we remember that one of our exponent laws says that we can move a base with its power across the fraction bar as long as we make its power the opposite. So 1/4 is equivalent to 4 to the power of -1. Well, that's advantageous because 4 to the power of -1 gives us common bases. Since we have identical bases, we can set the powers equal to each other. And now we have a one-step equation. Divide by 2 on both sides. X is equal to -1/2. (27 to the x minus 2 is equal to 729. All right. Well, now we got a little bit of work to do. 27 squared is actually 729, but that's not one that we really memorize or tend to know. We're going to go ahead and use it because I know it. Well, 27 squared is 729 is equal to 27 to the x minus 2. We have common bases, so we can set the powers equal to each other. Oops, sorry. X minus 2 is equal to 2. Add 2 to both sides. And that gives us an x that equals 4. But let's suppose that we didn't know that 27 squared was 729, and we needed to simplify this just a bit to make it easier. Well, I would probably recognize that 27 is 3 cubed. And that's one that we memorize, and most of us just know intuitively very quickly because it is a small cube and it's easier to remember. So 27 is 3 cubed raised to the x minus 2, which would simplify to 3 raised to the 3x minus 6. And since I have a base of 3 over here, you should be able to take our 729 and divide it by 3. And 729 divided by 3 is equal to 243, to which we can again divide by 3, which is equal to 81, to which we can again divide by 3. Which is equal to 27, so we can again divide by 3. Which is equal to 9, which we can divide by 3, which is equal to 3, which we can divide by 3, and we finally got down to our 1. Well, since we got down to our 1, that means that all of these 3's multiplied together equals 729. I see 6 3's, so that would be equal to 3 raised to the 6th power. Again, I have bases that are equal, and so we can set our powers equal to each other. 3x minus 6 is equal to 6, where we would add 6 to both sides, and 3x is equal to 12, where we would divide by 4, and x is equal to, divide by 3, and x is equal to 4. Sometimes I get the answer stuck in my head, and I just start writing numbers. Either way we did this, we ended up with the same solution. One involved me knowing the 27 squared is 729. The other, we broke both sides of the equations down to a very small base. All right, solve. 25 times 2 to the x minus 2 is equal to 50. Now, our natural desire is to want to multiply these two together. Remember that your order of operations, PEMDAS, parentheses, exponents, multiplication, division, addition, subtraction. We cannot do any multiplication and division until we have first cleaned up the exponent. But we cannot clean up the exponent because it's got a variable in it, which means we're not really trying to follow order of operations forward. Rather, we want to solve for the variable by following our order of operations backwards. So one of the things I do recommend students do is put your exponent in parentheses so that you hopefully realize you've got a value next to a parentheses. And anytime you have a value next to the parentheses, you can divide by that value in front of the parentheses. 25 over 25 becomes 1, so it will simplify out what you do to one side of the equation, you have to do to the other. So 50 divided by 25 gives me 2, which is equal to 2 to the x minus 2. Now another thing I want you to remember is anytime you have an integer by itself, its power is 1. So we have like bases, x minus 2 is equal to 1. We add 2 to both sides. X is now equal to 3. And we move on to the next problem. 5 to the x plus 1 times 5 to the 4th is equal to 125. Well, the first thing I realize is 125 is 5 to the 3rd power. The other thing I'd like for us to be in the practice of doing is simplifying any exponents that have common bases. Since this side has common bases, The base is the same. We can add the powers. 5 to the x plus 1 plus 4. So we can clean that up a little bit further. 5 to the x plus 5 is equal to 5 to the third power. And now again, we have common bases. So we can set the powers equal to each other. X plus 5 is equal to 3. Subtract 5 from both sides, and x is equal to -2. Exponential word problems. Now we're going to use a couple formulas for exponential word problems. The basic formula is f of t is equal to a sub 0 times r times t. And before we go too much further with this, I want us to define some of these terms. Now, f of t, we've used since our 7-8 years. That's just our understanding that we're dealing with a function with the input value of t. Function with the input value of t. Now, f of t is a fancy way of saying y. We also recognize that the y is the output. So it's generally our solution that we are looking for with any given equation. All right, next term, a sub 0. A sub 0 is not something we spent a whole lot of time talking about, but we did talk about a sub 1 and a sub 2 and a sub 3 when we did sequences. And you remember that a sub 1 was your first term, a sub 2 was your second term, a sub 3 was your third term. So if those are your third term and your second term and your first term, what are they the first, second, and third term from? They are the first, second, and third from some given starting point. So I often think of this kind of like a board game. When you have a board game, you start at start, you roll the die, and you move from the starting position. So a sub 0 is our starting position. All right, the R. R in most common formulas generally represents a rate. Now you see a rate expressed most typically in the word problems as a percent. Sometimes it's not expressed as a percent. So this particular formula is for a rate that is not expressed as a percent. Well, how do we not express a rate as a percent? We can double something, we can triple something, we can quadruple something, we can multiply something by 5. So that would be a rate that is not expressed as a percent. Now t. T, like we said, is our input value. All right, our t is representing the amount of time that passes. So we use this particular formula quite often with Petri dish problems. You also see it with population problems that do not give a rate as a percent. Appreciation equations. Now, this is often used with population. Yes, there are other things that it can appreciate. You can buy fine jewelry and it can appreciate. You can buy playing cards and they can appreciate. Notice the only real difference between this formula and the previous is that we have a 1 plus. That 1 plus is going to help us account for the increase in value of whatever item we are considering. The rest of our terms are identical, so I'm not going to go over them again. Appreciation problems in which you are given the rate as a percent use this formula. Now, if we are given the percent 15%, you're not going to put 15% with a percent sign in for the rate. Just as you have in previous years, anytime you have a rate that's expressed as a percent, you're going to change it to a decimal, 0.15, where you will take the decimal equivalency and plug that into the equation. Depreciation. Depreciation uses a nearly identical formula, The only difference is instead of adding from 1, we are subtracting from 1. Well, that should make sense because appreciation, I'm increasing in value, so I would add to something. Depreciation, I'm decreasing in value, so I would subtract from something. Depreciation problems in which you are given the rate as a percent, again, you're going to change that percent to a decimal. And then you will solve the given equation. So let's practice. From 1990 to 2000, the population of California has grown by 1.28%. The population in 1990 was 29,816,591 people. What is the total population in the year 2000? So before we do anything, let's identify our terms. A sub 0, where are we starting? That's going to be 29,816,591. Well, what is our rate? Our rate is 1.28%, but remember we don't want it as a percent, we want it as a decimal. So we're going to move the decimal over 2 places to express it as a decimal value. So 0.0128. And then lastly, the time. The amount of time that passes by. Well, we're looking for the year 2000, but we're not looking for 2,000 years because we don't have 2,000 years from our starting point as our reference data. Rather, our reference data started in 1990. Well, if 1990 is my 0 time, how many years have increased from 1990 to 2000? That would be 10. So 10 is our amount of time. Now that we have our variables identified, we can plug them into our formula. F of t, where t is the amount of time, and we just called that 10, is equal to a sub 0, which is 29,816,591, is getting multiplied by 1 plus the rate, 0.0128. And that's getting raised to the amount of time, the 10th power. Now, at this point, I'm fine with you using your calculator because these are rather messy exponents to multiply by themselves. And 2 million or 29 million is a pretty large number, so you're probably going to want to use your calculator anyways, just to keep you from having to multiply out all these numbers. So we'll do our 29,816,591 times 1 plus 0.0128. Close your parentheses. And then remember we talked about in class there was an X button raised to a box. That allows you to raise to a particular value where we want to raise to the 10th power. So f of 10 is going to be equal to 33,860,620 people and 0.69 of a person. Now, obviously, we can't have 0.69 as a person, so I would probably recommend what is the total population in 2020 or 2000. In 2000, the population let's see, is approximately 33,860,620. Just go ahead and truncate your answer and get rid of that decimal because we can't have 0.69 of a person. Next, an new all-terrain vehicle, ATV, costs $800. The value of the ATV decreases by 10% each year. Write an exponential decay model for the value of the ATV in dollars after 5 years. So again, let's identify our variables. A sub 0 is our starting value. R is our rate, so let's find it. That's 10% written as a decimal, so move the decimal over 2 places. So that's going to be a 0.10. Let's see, our amount of time. Time is given, so after 5 years. Well, it looks like we can start plugging in information. f of the amount of time, 5, is equal to a sub 0, which is 800, times 1 minus 0.10 raised to the 5th power. So again, we have the information. We can plug it into our calculator. 800 times 1 minus 0.10 is 0.9 raised to the 5th power. And so f of 5 is going to be equal to $472.39. It has had some depreciation. Number 3, write an inequality for the situation. Notice we've got a couple of cautions going on in this one. Inequality, inequality. A colony of rabbits in the wild doubles their population every year. Well, doubles. What does that mean? It means we're using our basic formula because we are not given a percent of increase or decrease. At the first observation, the scientists found 5 rabbits. Well, that's pretty good to know. That would be, sounds like to me like a starting point. So a sub 0 is equal to 5 rabbits. The rate is equal to 2 because it's doubling. After how many quarters will there be more than 40 rabbits? Well, how much time is passing? We don't know. That's the unknown there. Well, if that's the unknown, what are we going to do with the 40 rabbits? The 40 rabbits is actually the output. That's the solution. And it's the output with an unknown time. So we're actually looking for the time. So we know the f of t value is equal to 40. So let's write our inequality. 40 has got to be something. We don't know yet. Let's see. We'll talk about that in a minute. A sub 0 is 5 times the rate, which is 2, raised to the amount of time. Okay. Well, I said it needs to be something. We want the how many quarters there will be to be more than 40 rabbits. So I want this value on the right to be more than 40. Remember, we're using an inequality symbol because we're not setting up an equation, we're setting up an inequality. This is one of those examples where we have a number in front of the parentheses, so I would recommend dividing by 5 on both sides first. 40 divided by 5, well, that's 8, is less than 2 to the t. Now, what am I going to do now? I could guess at values of t. That would be one way of doing it, which is actually pretty simple for this type of a problem. But more specifically, I see that 2 has got, or sorry, the right term has got a base of 2, and I can make 8 become a base of 2 pretty quick and easy, because that's one of our perfect cubes that we've memorized. 2 to the third is less than 2 to the t power. Well, just like in an equation, if our bases are equal, our powers are equal. Well, if our bases are set in a particular inequality, our powers can be set in the same inequality. 3 is less than t. But we don't like to have a variable on the right side with an inequality. So we're going to move it to the left. And when we move it to the left, or we flip the entire inequality, we also need to remember to flip the sign. So t must be greater than 3. After how many quarters will there be more than 40 rabbits? After more than 3.